The learning objective in this podcast is to figure out how to write Lewis structure, their significance, what is the connection between resonance and Lewis structure, and what's the significance of formal charges. So before we start Lewis structure, we have to understand that atoms bond for one sole purpose, and that purpose is that the bonded state is more stable than the unbonded state. And the way stability is decided is by lowering of energy. So in a bonded state, the molecule or the formula unit has lower energy as compared to unbonded state, and that is why all the bonding happens. As we talk about stability and lowering of energy, there is one rule that plays a big part that's called Octet rule. And scientists have seen that atoms that have complete octet or have 8 electrons in valence shell tend to be more stable or tend to be of lower energy than the atoms that have less than 8 electrons in their valence shell. Valence shell refers to their outermost shell or energy level, and in valence shell there are only S and P sublevels, and S sublevel, as you recall from chemical bonding, can have up to 2 electrons and P can have up to 6. Hence you can have maximum of 8 electrons. D and F sublevel are never present in the valence shell because they are present in N-1 and N-2 sublevels. So atoms tend to gain, lose, or share electrons to complete their octet. Now there are exceptions to octet rule on both hands. There are atoms that are happy or stable in less than 8 electrons like hydrogen and helium. These are happy with less than 8 electrons, and then there are atoms that expand their octet or are more stable having more than 8 electrons in their valence shell. And we'll look at both of them in a little while. Now let's talk about Lewis symbols and clarify our concept of valence electrons. Valence electrons, again, to repeat, are the electrons in the highest energy level that are involved in bonding. All elements in a group have the same number of valence electrons. If you remember, group 1 elements have 1 valence electron. Group 2 elements, alkali, earth metals, have 2 valence electrons, and then transition metals can have variable valency or amount of electrons that they can lose, and we can talk about it a little later in the podcast. Now how do we write Lewis symbols? Lewis symbols are also called as electron dot symbol, where every valence electron is represented as a dot. You write the symbol of the atom in the middle. You start placing the valence electrons as dots around the symbol. The thing to remember is you do not want to pair the dots till each side has had one dot. For example, X, then you put 1 electron on each side, and then you start doubling the electrons. Okay, so if you have X as your element, you place 1 electron on each side, and then you start pairing them to complete the octet. No atom will have more than 8 valence electrons. And this works generally for representative elements, because transition metal elements, their d and f orbitals are also overlapping, so their s and p s electrons are lost first, but their n-1 d or n-2 f might be lost as well. Hence they show variable valency. Now just a quick understanding check at this point that you can draw Lewis symbol for carbon and nitrogen. Let me draw carbon with you, and nitrogen you can draw on your own. You know from periodic table that carbon has 4 valence electrons, so you'll put 4 electrons around it. And I'll leave you to draw nitrogen on your own. Now transition metal atoms can form variable valency cations +1, +2, +3. Let's take, for example, chromium. Chromium can have S1D5 and copper has S1D10, and this is NS1 and N-1D. This is NS N-1D. From chromium, first of all, it loses one s electron because it's farther out, but then to form 3+, it can lose more than one electron. Similarly, copper can lose its 1s electron, or if it's forming 2+, then it can start losing its d electrons as well. I might have switched the copper and chromium around, so check the electron configuration. Now, how do you draw Lewis structures, and what are Lewis structures? Lewis structures are representation, almost a shorthand way of showing how the lone pairs and bonded pairs are arranged and electrons are shared to form a molecule. Lewis structures are generally used for covalently bonded substances, but they can also be used to represent ionic substance. So just a refresher from the last podcast, if for lithium chloride, which is an ionically bonded compound, how do you know that? Because lithium is a metal and chlorine is a non-metal. So metal is present, hence it is an ionic compound. Now if we want to draw its Lewis structure, how would we draw it? We'll draw lithium with a positive charge, and around chlorine you'll make 8 electrons with a -1 charge. So that's lithium chloride. That is for an ionic compound, but if you want to draw Lewis structure for a covalent compound, there are 5 steps I recommend that you go through. Step 1, you find total number of valence electrons in the system. So here carbon has 4 valence electron, oxygen will have 3 times 6. Please note here, I am not counting the electrons it needs to make up its octet. It is how many valence electrons an atom has. For example, oxygen has 6 valence electrons, but it needs 2 to complete its octet. We are talking 6 valence electrons here. And then if it has a negative charge, then you add that charge because the system has that many excess electrons. And if there's a positive charge, you subtract it because the system has that much lesser electrons. So how many valence electrons are present in the system? 24 electrons. Now what we're going to do in the second step is we look at how many electrons does each atom need to be heavy. Every atom except for hydrogen and helium and beryllium and boron are happy with 8. Hydrogen and helium are happy with 2, beryllium is happy with 4, and boron is happy with 6. And these are the exceptions you will need to memorize. So in this case, for carbonate 2-, 8 for carbon to be happy, 3 times 8 for oxygen to be happy, and we don't include the charge here. So that's 32 electrons. The next step, to calculate how many bonds are there in the system, so you do step 2 minus step 1 divided by 2. So 32 minus 24 divided by 2 gives you 4 bonds. The nice thing about this stepwise approach is it tells you exactly how many bonds, so you don't have to do hit and trial. Now the next step is you draw the central atom, which is least electronegative or most electropositive in the middle. A hint here, if it is CO3 2-, generally C goes in the middle, but it's always good to check that you are drawing your least electronegative atom in the middle. So now you'll draw carbon and you put each oxygen around it with a single bond, but we have a problem. What's the problem? There is a double bond, and you put a double bond someplace, and then you complete every atom's octet. And the last part, if it is an ion, then you put brackets and charge around it. And the last part is accounting, where you need to make sure that you have as many electrons as you started with. If you recall from step 1, you started with 24 electrons. Let's count to see in this structure that you have 24 electrons. So 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this is correct structure. Now this double bond could have been drawn over here or over here as well. So that's an example of how to draw Lewis structure, and you can practice drawing more Lewis structures here. The overall view here is you first take the collective number of electrons present in the system, then you give each atom the electron it needs to be happy, and you figure out, first of all, you figure out how many bonds are there to bond to the central atom, each of the side atoms, and then you complete each individual atom's octet. So that's kind of the thought process in these 5 steps. And I can tell you ammonia structure is, there's a lone pair on nitrogen is like this, Cl2 is like this, and don't forget to complete the octet. You can draw a single line for a pair of electron, or you can draw 2 dots. Each is the same, CH2Cl2, so you can either draw both the H's here and Cl's here, or you can switch them around. They are isomers of each other, and either way is fine. And then NaCl is an ionic compound, and you can draw it. And these are some more. Now there are exceptions to octet rule. Remember, the first exception you got to remember is hydrogen, helium are happy with 2, boron's happy with, beryllium is happy with 4, and boron's happy with 6. So remember that. There are also odd electron molecules like NO and NO2. These molecules, they have an odd electron, not a paired. So in step 1, how many valence electrons? You'll get an odd number. And as you're trying to figure out the bonds, you'll get half a bond. You will round it up for number of bonds. So if you get 3.5 bonds, it is really not 3.5. You'll take it as 4 bonds, okay? Now, these are the ones with the incomplete octet. There are exceptions to the octet rule on the other end, which is larger than 8 electrons. Starting period 3, because of the d orbital, it is possible for central atoms to have more than 8 electrons. And sometimes having more than 8 electrons makes a molecule more stable than having 8. And such exceptions occur in case of PCl5, SF6, to name a couple. There are many, many more. How do you know if it is an exception on the expanded side? So if you follow the step, your number of bond will come out to be lesser than minimum number required to attach each side atom to the central atom. For example, let's do the steps here. First, number of valence electron, phosphorus is 5 and chlorine is 7 times 5. So that's 40 electrons. How many does it need to be happy? 48 electrons. And how many bonds does that give you? That gives you 4 bonds. Now you have 5 atoms around central atom. 4 bonds not going to cut it. That's how you know it's an expanded octet. If that happens, you go to plan B. You put phosphorus in the middle and attach each of the chlorine by a single bond to the central atom. Complete each atom's octet except for central atom, which will have more than an octet, and then you'll count to make sure that you have 40 electrons, and here there are 40 and your structure is complete. What if you had started with 42 electrons, but your structure was only coming out to be 40? Then you'll put a lone pair on the central atom. If there were 44, you'll put 2 lone pairs on the central atom. So any extra electrons get put on the central atom as lone pairs. And you can now try and draw SF6 molecule on your own. The last thing in this podcast is formal charge. So what happens is, there is a possibility to write different Lewis structures for the same molecule or same ion. Now, which is the correct Lewis structure? To answer that question, we employ something called as formal charge. Formal charge is not a real charge, it's an imaginary charge. That gives us guideline or helps us figure out if you can draw multiple Lewis structure, then which is the correct Lewis structure for your atom or your molecule or your ion. And how do you calculate formal charge? And it might seem a little confusing as I'm reading the rules, but when I take example with you, it'll be very clear. So these are some guidelines to calculate formal charge. You assign the unshared or lone pair to the atom on which the lone pairs are present. Half of the bonded electrons go to one atom, other half go to other atom. Okay, and then to figure out formal charge, the formula is, you see how many valence electrons are present in the free atom. You can figure this out from the periodic table, minus number of non-bonding and minus half of the bonding electrons, and that's the formal charge on an atom. Again, to remind you, formal charge is used to help us figure out the correct Lewis structure. It's not a real charge, it's an imaginary charge. Formal charge is calculated for each atom, not for the whole molecule or ion. You calculate formal charge for each atom. Now, once you're done calculating formal charge, how do you figure out which is the correct structure? And these are the two important guidelines that help us determine that. The most stable Lewis structure is the one where the formal charge on all atoms is closest to 0. And we are talking the absolute value of charge. -1 or +1 are both considered 1 off from 0. The second guideline is, if different elements in a molecule or an ionic compound or in an ion have same formal charges, then the correct structure is the one where the more negative formal charge is assigned to the more electronegative atom. Now let's take an example to do it together so you can see what I'm talking about. Let's take SCN- for example. So step 1 is how many valence electrons are in the system. 6 for sulfur, 4 for carbon, 5 for nitrogen, and 1 for a -1 charge. So that's 16 electrons. Step 2, how many does it take to be happy? These are all standard atoms, so 8 times 3, 24 electrons. How many bonds does that make? 4 bonds. Now we have a problem. Actually, we have more than one problem. First of all, what to put in the middle? You can put SCN. You know the least electronegative goes in the middle, so we don't really have to put S or N in the middle because it will not be supported by formal charge. So you can go with that. Now with that, you have 4 bonds. So you have some options. You can do 3 and 1, or you can do 1 and 3, right? And let's complete the octet for each of these. I like to draw lines so the dots don't get confused by some aberration in the paper. Now if we were to calculate formal charge for each of these atoms in each of the structure, and let's not forget the bracket and 1 minus charge because this is an ion. So these are the 3 Lewis structures that we think could be right. Now let's look at the formal charges of each. Sulfur has in an atomic form has 6 valence electrons, so 6 minus, and how many has it been assigned in this structure? 1, 2, 1 lone pair, 3, 4, and half of the bonded pair, right? So 1 and 1, so 6 minus 6, 0. Carbon is 4 minus, again half of the bonded, so 4 minus 4, 0, and nitrogen would be 5 minus 1, 2, 3, 4, 5, 6, -1. So 0, 0, and -1. Similarly here, the formal charge will be 6 minus 1, 2, 3, 4, 5, plus 1 on this sulfur. This is 0, and here this nitrogen is 5 minus 1, 2, 3, 4, 5, 6, 7, so -2. So here the overall formal charges, if you take absolute value, 2 and 1, 3. So this definitely is not a very good structure as compared to first, where the sum of all formal charges, absolute value is just 1. Now let's look at the last one, 6 minus 1, 2, 3, 4, 5, 6, 7. So -1, 0, and nitrogen has 1, 2, 3, 4, 5, so 0. So this structure is not a good one because there's too much formal charge, but both these structures, let me number them, 1, 2, and 3. The first and third structure both have formal charge of 0, 0, -1, or -1, 0, 0. So now which is the correct one? Remember the second rule, where the negative charge is given to more electronegative atom. And which is the more electronegative atom? Nitrogen is more electronegative. So the first structure is the correct one. This is how formal charge is used in predicting the correct Lewis structure. And the last thing is resonance structure. Remember, as we drew carbonate structure in the previous slides, we got 4 bonds. Remember? And carbon goes in the middle and we have oxygens around them. So our dilemma was where to put double bond, and I told you could put it here or you could put it at the other end, or you could put it with the third carbon, third oxygen right here. This type of traveling double bond shows resonance. If you were to complete octets here and figure out formal charges, you will notice that formal charge in all these 3 structures is the same. So these 3 structures, none of these is a better structure than other, but they are all equivalent structure. We call this phenomenon as resonance. When a molecule or an ion can have more than one correct Lewis structures, we call it as resonance. So the question might be, what is the correct structure? If you could get microscopic vision and look at it, what will you see? Will you see carbonate as the first one, second, or third one? Well, you'll see probably somewhere in between, or a mixture of all 3. So the electrons will be moving about and they'll be in a position somewhere in between these 3 positions. So that is called resonance. The best way to identify resonance is look for a traveling double bond. And with that, this podcast comes to an end. Thank you for listening.